Well, so before discussing about other challenges, let us see why at millimeter wave frequencies power handling capability decreases and why loss increases at millimeter wave frequencies. So, there are many sources, but because of the reduced size of the waveguide or the waveguiding structures, we will see that power handling capability and the loss it increases. So, let us consider a rectangular waveguide. So, this is the cross section of a rectangular waveguide. Let us say it is supporting TE10 mode. So, for this TE10 mode, if I plot the electric field strength from left to right side, so this is the electric field configuration for TE10 mode. So, it is maximum on the mid plane, and then if I go left or right side, the field strength decreases. Now, I am considering one more rectangular waveguide, but its thickness is much smaller compared to this, and it is also supporting similar mode TE10 mode. So, we have perpendicular electric field components which varies sinusoidally along its width. Now, the difference between 1 and 2 is that only thickness it changes, its width remains same. So, if I send now 1 watt of power through rectangular waveguide 1 and the same power through rectangular waveguide 2. So, now if I calculate the electric field values, so obviously in the first case we have much smaller electric field value, and whatever current we have, maximum current on the mid plane on metal surface. So, obviously that will be much higher for case 2. So, since the current component is higher, we are expecting more metal loss from case 2. So, not only that, electric field value as well as the loss both are increasing. So, power handling capability it will decrease for case 2 as well as loss will increase for case 2. So, this is one conceptual explanation why loss increases with reduced height or with the decreasing cross sectional area. If I consider a microstrip line, for example, it is showing a cross sectional view of a microstrip line. So, this is the top metallic strip and this is the bottom metal which we call the ground, and in between we have dielectric material. So, in this case the strip width is much smaller compared to lambda g. So, the energy, electromagnetic energy, mainly it lies just below the strip, and if I draw the electric field, it looks like this. So, inside the dielectric only I am using a small area for energy propagation. So, again if I send 1 watt of power through microstrip line, what we expect compared to rectangular waveguide? In this case, we will be having higher electric field value and higher surface current density. So, power handling capability will decrease further and loss will increase further. So, if I design this rectangular waveguide now, let us say at millimeter wave frequencies. So, you know that the dimension along x it depends on wavelength. For TE10 mode at cutoff frequency this width, it is approximately lambda naught by 2. So, if that is the case, then if I design one rectangular waveguide, let us say at 6 gigahertz, and FC this is equal to 6 gigahertz case 1, and in the second case FC is 60 gigahertz. So, what we expect for the second case, the broadside dimension of the waveguide is 10 times smaller than the first case. So, it will provide high loss, and not only that, power handling capability will decrease for the second case. So, the conclusion is then the if I decrease the cross sectional area of any guiding structure, in that case we will have higher loss and lower power handling capability. So, now let us go back to the challenges. Next is antenna. It can be resonating antenna or it can be travelling wave type antenna. So, whatever we design at millimeter wave frequency, it will give you very low efficiency, because whatever power you are going to feed to your antenna, so a part of that will be radiating and another rest part it will be absorbed in the antenna structure itself, which is due to the loss. So, since at millimeter wave frequencies loss increases, antenna efficiency will decrease or radiation efficiency will decrease. So, it is a problem actually at millimeter wave frequencies. So, typical antenna efficiency it can be as small as 10% to 20%. So, that means whatever power we are feeding to antenna, only 10% is being radiating to space. So, not only that, if we go for on chip antenna design, let us say we are designing the antenna on silicon. For silicon, dielectric constant is very high, almost 12. So, if you just place one resonating element on silicon, so instead of radiation in space, almost all of the power will be absorbed in silicon. The effect is due to surface wave generation. We will see later what is surface wave. So, this type of problem we will be facing at millimeter wave frequencies. So, we have to then use some alternative ways how to reduce these losses, how to improve the gain of the antenna. Next is the filtering function. So, filter typically use low loss resonators, and since we already discussed that if we really want low loss resonator, we do not have any other option than increasing the volume. So, for small size applications, then filter design of filter it is a challenge. Next, RF electronics part. So, loss it increases system noise figure. So, what is noise figure? Okay, so let me show you by using some diagram. This is another important quantity, noise figure. Let us say we have a 2-port network. It can be anything. It can be a filter, it can be a power amplifier, it can be any 2-port network. This is port 1, this is port 2. So, it is receiving some signal at port P1, and then the signal whatever we are collecting at port 2. So, let us say the SNR at port 1 it is given by the signal to noise ratio at port 1 it is given by SNRI, and the signal to noise ratio at port 2 it is given by SNRO. So, now if I take the ratio SNR at the input and SNR at the output. Usually we represent it in decibel scale, we call it the noise figure. So, usually the noise figure, it is represented in decibel scale, 10 log 10 SNR at the input divided by SNR at the output in dB. So, for a lossy system, for any given passive network, let us say a filter, it will increase the noise figure. Why? Because whatever signal is coming at the input port, due to the loss, the signal component will be attenuated further, and at the same time this component will add some noise. So, at the output total noise contribution is increasing, but total signal strength is decreasing. So, as a result, what we expect, that noise figure will increase. So, at millimeter wave frequencies, this term noise figure is very popular. By this we can understand how noisy the component is. It may be any active components like power amplifier, low noise amplifier, mixer, or it can be also any passive element like filter, coupler. So, for passive elements, usually the noise figure, this is equal to the insertion loss of that components for passive element. So, insertion loss is nothing but S21 in dB. So, let us go back. So, then we see that at millimeter wave frequency loss increases. So, it increases the noise figure of the component. So, one way to decrease the overall noise figure of any transmitter or receiver is that the first element of a chain of components of the let us say for receiver, if I start from antenna, just after antenna we have low noise amplifier, then mixer component. So, the first element should provide minimum noise figure, and it should be placed at as close to antenna as possible, so that we can decrease the overall noise figure of the system. And finally, the system must be cost effective, because if we use group 3, group 5 semiconductor material like gallium arsenide to fabricate millimeter wave system, it is not cost effective. So, that is why till now it is popular only with the defense sector, who can afford this expensive system. So, if we really want any consumer applications, we have to find out low cost solution, and that is possible if we fabricate the same system using silicon germanium technology or CMOS by CMOS technology. So, already some of the university groups and some research labs, they did it at 60 gigahertz using silicon technology. So, next is packaging, another important issue. So, whatever components we are designing, we have to put it under some packaging to protect it from severe weather conditions, and we have different packaging systems. One is called multi-chip modules. So, where basically different chips for different functions are integrated together in one single chip, and from and then it is put under one single package. So, from outside you can't understand that inside there are many chips. So, this MCM or multi-chip modules, it can be fabricated using low temperature co-fired ceramic technology, or more popularly known as LTCC, using microwave chip on flex. So, basically it is a one type of flexible laminates. Also we can use conventional printed circuit board technology or laminates to integrate these multiple chips. And next, then how to connect the chip with the other components. So, for that we have to use some sort of bonding. So, wire bonding, or it can be flip chip mount, we will see later. At millimeter wave frequencies, usually wire bonding is lossy, flip chip mount is less lossy, but it has some additional problem of power leakage and coupling and generation of surface wave modes. So, this is showing a typical scenario, one on chip antenna. You can see the copper part fabricated on silicon, but the problem is that if we directly fabricate one antenna on silicon, most probably it is not going to radiate anything. So, almost all of its power it will be absorbed by the silicon. So, then how we can make it radiate? So, one alternative solution is that use one air cavity just below this antenna structure. So, this right hand side picture actually showing that air cavity, and this antenna then it is placed on the air cavity. So, now it will radiate into space. So, this is one solution how we can improve the gain of the antenna. So, now the second picture, this is showing a silicon based low cost 60 gigahertz transceiver. So, this antenna now it is being integrated in the single chip, where we have other components like low noise amplifier and switching and everything, all are millimeter wave components. So, when we integrate antenna inside the same chip, we have to take care of many factors. For example, this antenna, it is a resonating structure, it has some fringing electric field in silicon and air. So, it can interact with other metallic part of this chip itself. So, then antenna it should be placed as far as possible from the chip. Not only that, if there is any metal part on this chip itself, then we have to use some sort of insulator in between antenna and the chip part, or simply we have to increase the separation between antenna and this chip part. Now, if I look at this chip, then the passive components, typically the inductors, it occupies very large area, and usually they are fabricated on the top metal layer of the chip. So, the coupling between the inductors and the antenna, it is expected to be maximum. So, sometimes that is why, to avoid that coupling between the inductor and the antenna, we use some sort of guard ring around the antenna structure, which will minimize the coupling between antenna and the inductors. So, you can also see this is since a silicon substrate. So, they are using that air cavity. So, this is the radiator, and just below it we have this 400 micrometer thick air cavity. So, it just below the air cavity we have antenna reflector cavity. This is just metallization on the cavity wall. So, which behaves as a reflector and further increases the gain. Now, let us say we are going for a practical design. We want to design some millimeter wave components at using some printed circuit board technology. So, for that we have to choose a printed circuit board first. What is printed circuit board? It is nothing but a dielectric slab, and it comes with a top and bottom copper cladding metal. So, if you take the cross section, a dielectric layer, it is sandwiched between two metal layers. And what is the thickness of dielectric? We have some standard thickness available, and just a few companies actually make these substrates, we call it substrate, and some standard dielectric constants also available. So, one of the popular company names is Rogers Corporation from USA. So, if you go through Rogers website, you can see that it is coming with some standard thicknesses as well as with some standard dielectric constant. So, for example, if I consider a typical substrate, its name is RT-Degroid 5880, its dielectric constant is 2.2. And if you go through Rogers website, you will find out some typical thickness like 5 mil, 1 mil equal to 1000 of 1 inch. So, 10 mil, 20 mil, 32 mil, some standard thicknesses are only available. You do not have any value in between. So, you have to choose first your substrate. So, how to choose your substrate first? So, we have to keep many factors, many parameters in mind when you are going to choose your substrate. So, for example, if I increase dielectric constant of the substrate, what will happen? The component size will decrease. Why? Already we discussed that lambda g, this is equal to approximately lambda naught by root epsilon r. So, if I design a resonator lambda g by 2 length at let us say in a substrate with dielectric constant 10.2, and we have one more substrate of dielectric constant 2.2. So, obviously, it will be of small size in 10.2 dielectric constant substrate. So, then obviously, we have some advantage, we can miniaturize component, but at millimeter wave frequencies already the component size is small, and not only that, if we go for miniaturization, we face one more problem. What is that? Loss increases as well as power handling capability decreases. Different substrate provides different loss values. That loss we quantify by using a parameter, we call it loss tangent of the substrate. So, we will see later. So, loss tangent, that is another important factor for any given substrate. Higher the loss tangent is, higher the dielectric loss is. So, when you are choosing your substrate for your application, you have to keep all these points in mind. And now, let us visit through Rogers page and find out how these specifications are given. So, for example, I am considering a typical RT-Degroid 5870 substrate and RT-Degroid 5880 substrate. So, this page I am showing from Rogers Corporation's website. This is the data sheet. So, you can see dielectric constant epsilon r, some suggested values are given. They are calling it the design value. For 5870, it is 2.33. For 5880, it is 2.2. And not only that, if I go to write, the suggested frequency range is 8 gigahertz to 40 gigahertz. So, they are specifying this dielectric constant value for design from 8 to 40 gigahertz. If I increase the frequency further, so that means dielectric constant may vary, it may not be fixed at 2.33 or 2.2. So, similarly, the dissipation factor or loss tangent, another name is tan delta. So, you see for 5870, they are suggesting two values 0.0005, this is at 1 megahertz, and below 0.0012, this is at 10 gigahertz. For 5880, these values are 0.0004 and 0.0009. So, you see as the frequency increases, what they are showing, the measured loss tangent values, they are increasing, but we will see theoretically loss tangent should decrease, but practically if I look at the measured values, loss tangent is increasing with frequencies. There are many other factors like what is the thermal coefficient of epsilon r. So, epsilon r, it is changing with frequency. Not only that, epsilon r, it is also a function of temperature. Consider any space based application. In space, the temperature can be as low as -60, -70 degree centigrade, or if any component is under constant sunlight illumination. So, the temperature can be as high as 100 degree or even more than that. We have a wide range of temperature. This component should support this variation. So, dielectric constant, whatever we are using to design that components, then it should not vary with temperature. In fact, there are only a few space certified components. For the space certified components, the dielectric constant or whatever change in dielectric constant, it is really small, negligibly small. So, depending on applications, you have to choose your substrate very carefully. For example, if you go for any space based application, you have to only choose space certified substrate. So, with this some there are additional parameters like what is the Young modulus of your substrate, what is the vapor absorption coefficient of your substrate, because if the dielectric it absorbs vapor, so water is very lossy, and if it absorbs vapor, dielectric substrate it will becomes very lossy. So, there are many other factors, so we have to keep in mind. So, in the next part we will see what are the different material properties at millimeter wave frequencies, and not only that, even at terahertz frequencies. So, sometimes we use the same materials for microwave frequency design, circuit design, and as well as for the millimeter wave frequency design. But then since already we know that dielectric constant it is a function of frequency, then how this material behaves at millimeter wave or sub millimeter wave frequencies. Okay, so we will take a short break, then we will start again.